In this article, we are going to learn diffraction. For this, the question will be, what is the diffraction of light? How does it differs from interference? What are Fraunhofer and Fresnel's diffraction? Or distinguish between Fraunhofer and Fresnel's diffraction? So we will answer for this one by one. First of all, let us see what is a diffraction. We have studied that light travels in a rectilinear direction, or light performs rectilinear propagation. What does it mean? In a given medium, light travels along a straight line. But here we are going to learn, in the same medium, the light is going to bend. Light is going to change its path. And this can be learned by taking some examples. Suppose this is the torch. From this torch, the flash of light is given out. Now you will find that this flash of light, it spreads up, it becomes broadened. Next, this way, here there is a bending of light due to the edges of this torch. Not only this, suppose that an object, it is kept in the path of this light. Then what happens? Suppose that a ray of light is traveling like this. Then here there will be a geometrical shadow. There will be a geometrical shadow. Now, due to the sharp edges of this obstacle, this light is going to bend. And it encroaches into geometrical shadow. At the same time, suppose that this is the source of light and this is the obstacle. Like this, and light rays are traveling like this. What happens? Here it is geometrical shadow. Here it is geometrical shadow. These are light rays. After touching to the slit or edges of the sharp object or obstacle, these light rays, they are going to bend. And there is an encroachment into its geometrical shadow. Here we have seen there is a bending of light. This bending of light, it is because of the sharp edges of the obstacle, and therefore such a phenomenon, it is called as a diffraction. Now, with this information, we will define diffraction. The phenomenon of bending of light. The phenomenon of bending of light due to sharp edges of the obstacle and its encroachment into its geometrical shadow, it is called as a diffraction. And therefore, here, first answer, the phenomenon of bending of light due to sharp edges of obstacle its encroachment into its geometrical shadow is called diffraction. Some examples we can give like this. The shining of peacock feathers if we see through white cloth, if we see the sun through white cloth, then a spectrum of seven colors is seen. There are many of the examples. Many times we are using this diffraction phenomenon. Next example I will tell you, that is a aeroplane at a certain height do not cast its shadow. Because of diffraction, the rays are going to bend and therefore no shadow is going to form. Next, before the sun rises, the rays are coming to us and we are getting the light. After the sunset, for a certain time, there is a light, because light is coming by bending the edge of the earth. So this way, this is diffraction. Next is, how does it differs from interference? Diffraction is different from interference. This diffraction phenomenon, it is different from interference pattern, and it is like this. Number one, in a diffraction, there is single source. In interference, minimum two sources are required. Next, in a diffraction, part of the wave is bending. In interference, part of the wavefront produces interference. For just to know how they are different, these 2 points I have given. Actually, there are many points. In interference, the intensity is remaining constant. In a diffraction, intensity of light is going on decreasing as the distance increases. Next, in interference, the width of, that is, width of fringe width or band width, it remains same, but in diffraction, this width is going to change. With this, we should proceed for next. What are Fraunhofer and Fresnel diffraction? First, we are going to learn Fraunhofer diffraction. Just now here we have seen there is an obstacle, there is a source, and here there is a screen. If the distance, what is the Fraunhofer diffraction? A diffraction pattern in which the distance of source and screen from obstacle is large is called Fraunhofer diffraction. Next, as the source is very long from the obstacle, the light is traveling, or light rays, they are traveling parallel to each other. When the light rays are traveling parallel to each other, the wavefront is called as plane wavefront. So the wavefront is plane wavefront. Next, third, here the light coming from sun, that produces Fraunhofer diffraction. Next, second, Fresnel's diffraction. Very simple. Here, a diffraction pattern in which the distance of source and screen from obstacle is large. And this diffraction pattern, it is called as a Fraunhofer diffraction. Now, if this distance is small, then it is called as a Fresnel's diffraction, and therefore in this first point is a diffraction pattern in which the distance of source and screen from obstacle is small is called Fresnel's diffraction. Next, second point. See here, as the distance is small, that wavefront, it is a spherical wavefront or a cylindrical wavefront, and therefore plane wavefront. Here I must correct this. Plane wavefront is used. Here spherical or cylindrical wavefront is used. And the third point, that is what? Here the light coming from sun, light from bulb or tube light. So by using these points, you can distinguish between Fraunhofer diffraction and Fresnel's diffraction. This is all about the Fraunhofer diffraction and Fresnel's diffraction. Now the next point which we are going to learn, that is the experimental setup for Fraunhofer diffraction. And for this, a question will be, draw a diagram of experimental setup. For Fraunhofer diffraction. How did the Fraunhofer diffraction it is taking place? To demonstrate this, we have to draw a diagram. This is a point source. Suppose this is the primary lens. This is the source of monochromatic light. The light rays are traveling in this direction. They are falling on the lens. When they are falling on this lens, they are going to produce the plane wavefront. This is the secondary lens. And here is a slit. This is slit. This is A. This is B. The slit width it is A. These rays, they are traveling in the form of plane wavefront. Suppose this is the screen. Now, see here, this plane wavefront, it is incident on this mirror, and therefore these rays which are parallel to each other, they are going to converge at a single point. This is suppose P0. P0 is the maximum intensity point. See here the steps to draw this diagram. Here one lens, it is kept, light from the primary source or a source of monochromatic light, it is falling on this obliquely. These light rays, they become parallel because of this lens L1. Next, these parallel rays, they are traveling further, but what happens? There is a slit of the width A, and through this slit, when this light is traveling, that time this light, it is getting converged at a single point at P0. Now when we consider the diffraction, or we have said that there is a bending of light, because of this bending of light from this slit, these light rays, they are going to bend, which is called as the diffraction of light. Now these rays, they are getting converged at a certain point. The rays which are bent, they are getting converged at a certain point, forming the next bright point. This is point P. So here, after diffraction, these rays, they are traveling in this direction, and due to this lens, they are getting converged at point P. At this time, they are making certain angle theta. This is suppose theta, this is suppose a theta, this is 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 theta, and this is theta. So with the same angle, they are getting diffracted on upper side, and due to this lens L2, all these rays, they are getting converged at a certain point P. Now, this is the first central maximum. This point P0, it is called as a central maximum. This point P, it may be a minimum or a maximum, and same way on this side, at a certain point, the diffraction pattern it is formed, and this way, it produces, or this is an arrangement to experimental setup for Fraunhofer diffraction. Now here there are certain labeling. Yes, monochromatic source. Next, L1, L2. Biconvex lens. Next, AD. Slit. Small a, slit width. Lambda, wavelength of light. Theta, angle of diffraction. P0, central maximum. Point P, minimum. First minimum, and this is what it is, screen. So this is the experimental arrangement to learn the Fraunhofer diffraction. This distance from this lens to the screen, it is F equal to capital D. It is F equal to capital D. So with this we will stop here. The remaining things we will learn later on.